Guys, there's some assumptions in this problem that maybe you don't know. So this was a trickier problem, and usually this is a problem that I go over with the class, but since I'm not here, here's a video of it. What you know, since first of all, we're talking about feet, what we know is that the acceleration from gravity, which is dv dt, is a constant, and it's negative 32 feet per second squared. So that's the acceleration due to gravity. So therefore, we could get an equation for velocity. So velocity is the antiderivative of acceleration. So to get an expression for velocity, the antiderivative of that is just negative 32t. And we're using t, not x, because t is the variable. But then it's plus some constant. Because remember, when you take the antiderivative, you always add a constant. Well, we can find out what that constant is. We can find out what this constant is because we know that initially the velocity is that. That means that the velocity at time 0 was 96. So we could find out what the c value is by saying that 96 equals negative 32 times 0 plus c, and this quickly leads to the fact that c equals 96. So then we get an expression for v. We get v equals negative 32t plus 96. Well, v is, if we say that s of t is position, v, our velocity, is the derivative of our position. So to get an equation for our position, we take the antiderivative. So that would be negative 32t squared over 2 plus 96t plus c. And we know that my position was initially 144, so when time equals 0, the position is 44. So therefore we can, quickly show that c is 144. So we get this equation. Position equals negative 16t squared plus 96t plus 144. So now I know everything about my acceleration, which is always a constant, my velocity, which is right here, and my position. So given any time, I can know my position, my velocity, and my acceleration, which is a constant. So now let's go ahead and answer those questions. Okay, so now to answer these questions, well, we've actually answered one of them already. Part A is the stone's distance above the ground after t seconds. Well, that's just our general equation for position. That's this right here. So that is our answer for part A. Oops. And then for part B, the length of the time the stone rises. Well, if we think about something going up, it's going to go up and it's going to slow down and slow down and slow down and slow down. And then at the very top of its path, the time that it takes to go up here is really asking the time that it takes for its velocity to become 0. Because after its once it comes to a velocity of 0, then it's going to start going down. So once its velocity is 0, that's the total time at which the stone is rising. So to answer B, we're just saying, when does my velocity equal 0? And so we get t equals 3 seconds. And for part C, it's saying when and with what velocity does the stone strike the ground. So there's two questions here. When is time, and what velocity? That's velocity. So let's answer the when. When it strikes the ground, when the stone strikes the ground, what we know, we're looking at like the instant right before it strikes the ground. So the instant right before it strikes the ground, its position from the ground is going to be 0. So we can just solve this equation for position, setting it equal to 0. I just used Wolfram Alpha to solve this, and the solutions that I got back were the following. So clearly we're looking at the positive solution. So that's the time that it takes. That's the when it hits the ground. And with what velocity, we're looking for the velocity at the time of 7.24. So just use our velocity equation. So you get negative 32 times 7.24 plus 96. Whatever that equals something. So that's the solution to this problem. It relies on an understanding of physics, and it also needs you to use your understanding of antiderivatives. But what you'll realize is that all of the physics equations that you've been using at one point in your life come from the idea that acceleration is a constant, and then from that acceleration we can just take the antiderivative to find the velocity, and then the antiderivative of that to get position. And so that's where all those position equations come from. And in fact, for those of you that want to keep listening, I think it's really interesting to keep it general. And if we said that we've got the acceleration due to gravity, and so that is dv dt, and so this is with a constant g. So this is if we're in free fall, and the only acceleration is gravity, and that gravity is a constant. So then we get that v equals gt plus some constant. Well, my constant is just whatever my initial velocity is, and this equals the change in position with respect to time. So our position then would be gt squared over 2 plus v naught t plus some constant, but that constant is just my initial position. And if I rearrange this, I get that position at any time equals my initial position plus my initial velocity times time plus 1/2 gt squared. And this is the main physics equation, which any of you that have studied any bit of physics have seen at one point for free fall. And here's where it's derived. It's all derived from the idea that acceleration has a constant g. Acceleration is dv dt, and v equals ds dt, and from that, taking antiderivatives. Pretty cool.